Hello to all, my name is Barış Kuseri, and today I'm going to present you my project titled as Permanent Magnet Temperature Estimation using convolutional and recurrent neural networks. There's a navigation bar on the side of the presentation, so you can also follow where we are at any time. Permanent magnet synchronous motor is a type of electric motor. This type of motor is widely used in many industrial applications because they demonstrate really good performance characteristics, especially in terms of torque density. Neodymium iron boron magnets, shortly neodymium magnets, are a type of permanent magnets which are widely used in this type of motors. Unfortunately, there is a risk of demagnetization in these permanent magnets, especially when the temperature is high. So we need to monitor the temperature of these permanent magnets during operating condition. However, there are no available non-invasive methods of monitoring the temperature of these permanent magnets. The solution to this problem, which is experimented in this project, is to estimate the permanent magnet temperature by using neural networks. In this project, I have used convolutional and recurrent neural networks. And once these networks are trained, and if they are showing good results, these networks can be implemented to the motor controller, so the permanent magnet temperature can be estimated during operating condition. The observations obtained are given here. They include temperature data of the permanent magnet, the ambient temperature, the coolant temperature, and stator, yoke, tooth temperatures and windings. Additionally, there are data on D and Q axis voltages and currents, and motor speeds in round per minute, and torque output. Next, I dispose some of the features that are presented in the dataset. The reason behind this is that not each feature in the dataset is available in real-life conditions. So to make the solution more realistic, I only need to use the features that are actually available. So the disposed features are stator yoke, stator tooth, and winding temperatures. And also I disposed the torque output because it is not also available in real life. So the features left to me is D and Q axis currents and voltages, the motor speed, and ambient and coolant temperature. Last thing I did as a part of pre-processing is the normalization. I normalized each feature among itself, and the normalization equation is given here. This equation, basically what it does is it scales the data in the feature between -1 and 1. This is done because when we normalize the data, it actually speeds up the training duration. Here, I want to present you the structure of my convolutional neural network. As can be seen, there are 4 layers. 2 of them are one-dimensional convolutional layers, and 2 of them are dense layers. As can be seen, this is my base network. What I mean is, this is the network that I have started my study. And I have taken these values as my variables, the values that have a code next to them, and I altered these variables to experiment with the performance output of these networks that I obtained. And I'm going to present you to performance outputs of these networks in the experimental results section. Here is the structure of my recurrent neural network. As can be seen, my base network has 3 layers. The first 2 are long short-term memory layers, and the last one is a dense layer. Again, here I have chosen the number of kernels of the long short-term memory layers as variables, in which I altered them to achieve a better performance. Next, I'm going to present you the performance criteria that I used to assess my networks. The first metric I have used is R-square regression score. And to calculate this, if we assume n samples, and yi hat is the predicted output for the ith sample, and yi is the real output, this score can be calculated by these equations. This score can be a maximum of 1.0, and it can be negative if the model is arbitrarily bad. And if the model constantly predicts the expected value of y, disregarding the input features, then this score gives out 0, as in the model doesn't actually work. Here are the experimental results. As can be seen, the R-square score for each network are very similar to each other. On the other hand, the training time of each network is significantly different. As can be seen, the base convolutional neural network, as can be seen in the first row of this table, is significantly below the training time for the other networks. Overall, the best network is the base convolutional neural network mentioned previously. This is due to the fact that this network's training time is significantly lower than the other networks. Each of the networks showed promising results in terms of R-squared scores. So the results suggest that this method for estimating the permanent magnet temperature is suitable for industrial applications. Thank you for listening to me.